In the previous video, we looked at more of a quantitative approach to Lenz's law and determining what the polarity would be for the voltage at different regions in time based on the sine wave. Now, let's take a look at this again, but instead of using the quantitative approach, let's use more of a qualitative approach and see if we can just intuitively understand why the voltage is going to be changing from positive polarity to negative polarity based on what's happening with the induced magnetic field. So in that first region, let's take a look first at that sine omega t. And we'll look at the sine omega t because that is what the magnetic field is going to be controlled by. So that sine omega t in that first time region is going to be a positive value because sine omega t is positive in that region. And in that region 1 of time, the magnetic field is going to be increasing. So the B naught sine omega t is positive, which means that the magnetic field is in the positive z direction, and it's also increasing throughout that entire region. Now, the induced magnetic field is always going to oppose the change. So B induced is going to oppose the increase in B. So to oppose B increasing, B induced should be in the opposite direction to oppose the increase. That means that the B induced is in the minus z direction, opposing the increase in B. So if it's in the minus z direction, we can use our right hand, put our fingers there, point them in that minus z direction, and when we point our fingers in the minus z direction, we can see that the thumb is going to be pointing along with the current from point 2 to point 1. So the current is going from point 2 to point 1, from minus to positive. So that means that the transformer voltage is going to have a negative polarity in this region. Now let's look at the second time region. And so in this case, we'll look at the blue sine wave, and we can see that the blue sine wave, the sine omega t, is a positive number still. So in this region, it's a positive number. So because it's positive, the magnetic field is going to be pointed in the positive z direction. However, the value of the magnetic field is going to be decreasing because in this second time region, sine omega t is decreasing the entire time. And the induced magnetic field, B induced, is always going to oppose change. So to oppose the decrease, the induced magnetic field is going to be pointed in the z direction because the B is getting smaller. So we're going to have an induced B, a magnetic field that's induced in the positive z direction to oppose that decrease. And we can put our right hand there along the loop, our fingers pointed in the positive z direction, and our thumb is going to then show us the direction of the current, which goes from point 1 to point 2. So from the positive to the negative terminal of our transformer voltage, which means that we're going to have a positive polarity in this second time region. Now for the third time region, we'll look at our sine omega t, and we can see that now sine omega t is going to be a negative number. So that means that because it's a negative number, the magnetic field is now pointed down. It's pointed in the minus z direction. And throughout this entire region, so in this time region 3, the size of the magnetic field is getting larger. So it's getting more and more negative. So it's pointed in the minus z direction, and it's getting bigger pointed in that direction. Now, the induced magnetic field will always oppose any change. And so because the magnetic field is pointed in the minus z direction and getting bigger in the minus z direction, B induced will oppose that change, oppose the increase in the minus z direction by pointing up in the positive z direction. So the induced magnetic field is in the positive z direction to oppose B getting larger in the negative z direction. Now, if we put our right hand there, our fingers pointed up in the z direction, and our thumb is going to be pointed along the direction of the current, which goes from point 1 to point 2. So from positive to negative, meaning that our voltage polarity is going to be positive because the current is going from positive to negative. Now, in the last region, our sine omega t is still a negative number, but it's getting smaller. So it is getting smaller and smaller throughout this region, and it's still negative. So B is pointed in the z direction, but it's getting smaller. And the induced magnetic field is going to oppose the fact that this B is decreasing. So we need an induced magnetic field that opposes the change. So because B is getting smaller and smaller in the z direction, to oppose that change, we're going to need an induced B that points in the minus z direction to oppose the decrease. So the induced magnetic field is in the minus z direction. Now, if we put our right hand there on the loop, our fingers pointed in the minus z direction, just like this, we can see that our thumb is going to show us the direction of the current. And the direction of the current is going to go from 2 to 1. So from the minus to the positive. And because of that, that means that the transformer voltage in this case is going to be less than 0. It's going to be negative polarity. The current is flowing from the minus to the positive. So overall, we are going to have these 4 different time regions in which we can see that the current is going to be changing direction. So in region 1 and region 4, the current is going to be going from the minus terminal to the positive terminal, so we're going to have a negative polarity. But in region 2 and region 3, it's going from positive to negative, giving us a positive polarity. This is the same result that we got from the quantitative method that we saw in the previous video. This method is more qualitative because we're looking at the direction of the magnetic field, determining how it's changing, and realizing that the induced magnetic field is always going to be opposing any change, which is what Lenz's law tells us is going to happen.